Hi everyone, good day. Welcome back to my channel. I'm Anna Raman. This day I will discuss to you about polar coordinates. First I will discuss to you the history of polar coordinates. First Greek used the concept of an angle and radius. The Greek was they used the concept of the angle and radius. So Hipparchus from 190 to 120 BC or before Christ tabulated a table of chord function giving the length of the chord of each angle, and there are references to his using polar coordinates as establishing stellar position. From Archimedes described his famous spiral, a function whose radius depends on the angle. Saint Vincent introduced the concept about polar coordinates privately in 1625 and published in 1647. From Cavalieri he published concept about polar coordinates in 1635 with a corrected version appearing in 1653. Cavalieri first utilized polar coordinates to solve a problem relating to an area with an Archimedean spiral. From Blaise Pascal, he used polar coordinates to calculate the length of a parabolic arcs. Caesar Isaac Newton and method of fluxions written 1671 and they published 1736. He was the first to look upon polar coordinates and 9 others coordinate system. Jacob Bernoulli and Acta Eruditorium 1691 used a system with a point on line, called the pole and polar axis respectively. Coordinates were specified by the distance from the pole and the angle from the polar axis. He extended to finding the radius of curvature of curves expressed in these coordinates. From Gregorio Fontana was accredited the actual terms polar coordinates and used by 18th century Italian writers. From George Piacox, the term appeared in English in 1816, accredited with a translation of Lacroix's differential and integral calculus. From Alexis Clairaut and Leonhard Euler are credited with extending the concept of polar coordinates to 3 dimensions. Here are the properties of polar coordinates. In mathematics, the polar coordinate system is 2-dimension. The 2-dimension coordinate system in which each point on a plane is determined by a distance from a reference point at an angle and reference direction. Polar coordinates describe a point in space as an angle of rotation around the origin of a radius from the origin. From Cartesian coordinate to the x and y components of a vector. From polar coordinates to the magnitude, length, and direction angle of a vector. The Greek letter theta is often used to denote an angle, and a polar coordinate is conventionally referred to as the quantity of r and theta instead of x and y. Sin theta is equal to y over r, or y is equal to r sine theta, and cosine theta is equal to x over r, or x is equal to r raised to the power of cosine theta. For example, Graph of the curve by r is equal to 2. All points with r is equal to 2 are the distance 2 from the origin. So r is equal to 2. Describe the circle of radian 2 with enter the origin. So this is the graph. So this is the r is equal to 2. So next, graph of the polar coordinates. The quantity of r is equal to theta by r is equal to 2 and theta is equal to pi over 2. So here is the graph. So this is the r is equal to 2 and from the curve this is the pi over 2. So number 3, find the equation of the line y is equal to 3x plus 2 in polar coordinates. We merely substitute r sine theta is equal to 3 third cosine plus 2 or r is equal to 2 over the sine theta minus 3 cos theta. So this is the graph. So this is the pi over 4 and padulong diri iyang arrow. So next, 4. Find the equation of the circle x 1/2 squared plus y squared is equal to 1/4 in polar coordinates. Again, substituting the quantity of r cos theta minus 1/2 squared plus r squared sine squared theta is equal to 1/4. A bit of algebra turns his onto r is equal to cos the quantity of t. You should try plotting a few the quantity of r and theta values to convince yourself that this makes sense. So 5. Convert 4 and -3 from the Cartesian to polar coordinates. So this is the quadrant and Cartesian coordinates and theta range. So from first quadrant, so in Cartesian coordinates, so this is the x and y and 0 degree to 90 degree. So in quadrant 2, from the Cartesian coordinates, so it's -x and y and 90 degrees to 180 degree. From the third quadrant, so this is the -x and -y and 180 degrees to 270 degrees. So in fourth quadrant, so from the Cartesian coordinates, so this is the x and -y and from the range is 270 degrees to 360 degrees. So quadrant 4 example, r is equal to the square root of -4 squared plus 3 squared. So let's solve. So -4 times -4 is equal to 16 plus 3 times 3 is equal to 9. Then 16 plus 9 is equal to 25. So the square root of 25 is 5. So that's why our r is 5. So theta is equal to tan raised to the power of 1. The quantity of 3 over -4 is equal to -36.87 degree. And convert so 4 and -3 from Cartesian to polar coordinates. So the theta is equal to -36.87 degrees plus 180 is equal to 143.13 degrees. So the final answer is our r and theta is equal to 5,143.13 degrees. So thank you for watching. Hoping you have a little learned from my discussion. So thank you and God bless. See you in my next discussion and don't forget to subscribe my YouTube channel. And